In this video, we'll be looking at how to calculate the mean, median, and modal averages of a set of data. Then we'll be looking at calculating the range of that data and using it to interpret how accurate those averages are. We'll then be looking at how to draw and interpret an ordered stem and leaf diagram. Lastly, we'll look at how to calculate averages from tables and grouped data charts. Let's start off with some definitions of what these averages relate to. The mean is the one that most people are referring to when they talk about an average. This is where you add up all of the data and you divide by how many pieces of data there are. It's a simple process that works well in most cases, but sometimes there's very good reasons not to use it. For instance, if we calculated the mean income of some random gathering of people in a room, we may get a fair average. However, if one of those persons is a billionaire, the mean average would look like they were all millionaires, which is doubtful. This is one of the reasons we can use the median average. The median average is the middle value once you put all the numbers in order. If your data set has an even number of pieces of data, then you're going to end up with two numbers in the middle. If this is the case, simply add them together and divide by 2 to get the median. This works well for data that's in the form of numbers. However, sometimes our data set could be made of non-numerical information. For example, eye colour, in which case the mode would be a good average to use. This is where you place them all in order, as for the median, and then identify the most common piece of data. Both the median and the mode are not influenced by outliers or pieces of information that seem distant from the majority of the dataset. However, this also means they don't take these pieces of data into account. The last piece of data that's useful when considering averages is the range. Whilst this is not an average, it does show how accurate our averages are. The larger the range, the less consistent our data tends to be, and this therefore lessens the accuracy of our averages to represent the data we're using. Let's see how we would apply these averages to a set of data. This data set refers to the amount of paper clips that Nancy has in 10 boxes. It gives us the amount in each box, and we're asked to work out the mode, median, and mean average, and the range. Let's first place them all in order from smallest to largest. A common mistake is to complete this with no regard to the number of pieces of data. And I've missed off pieces of data in the past, so I've taken to listing the data in order under the current list. This way I can use the place settings to ensure I have the same number of pieces of data in my ordered set as in my original set. Therefore, I've listed them as 11, 11, 11, 12, 13, 14, 14, 14, 14, and 15. Every piece of data in the original set has one underneath it, so I can be sure none are missed. To calculate the mode average, we can see that there are 4 14s, so we can state that this is the mode. If there'd been more than one piece of data with the same amount, I'd list them as modes, plural. If there were 2 pieces, for instance, I could say they were bimodal. To calculate the median average, we can either tick them off alternately from either end like this, which is where we end up with 2 numbers in the middle. This is because we started with an even amount of numbers. If this is the case, we can add them together and divide by 2, in effect finding the average of those 2 pieces of data. In this case, 13 plus 14 divided by 2 would give us 13.5. We could also do this by finding the place of the median, which will come in useful when we deal with grouped data. In order to find this, we take the amount of data, in this case 10, add 1 and divide it by 2. As you can imagine, doing this with an odd numbered data set will give us an integer or a whole number place in the data set. As we started with an even numbered set of data, we're going to get the 5.5th place, which we know can't exist. So we should recognise that our median is going to be between the 5th and the 6th piece of data. If we count along again, we find that it will be between 13 and 14, and therefore we also get the answer of 13.5, which is no surprise. To calculate the mean average, we simply add up all the numbers to get 129, and then we divide it by 10, as there's 10 boxes. This gives us a mean average of 12.9. So we've calculated our three averages and got three different numbers. Now this can occur quite often, as we're looking at different processes. The median and the mode are not affected by the first three numbers being 11. Therefore, they're larger than the mean. To enable us to find out how consistent these numbers are, we can calculate the range, which is the largest number, 15, subtract the smallest of 11. This gives us a range of 4. In order to interpret this data, we need to consider whether this range is large or small in the context of the data. If we were talking about 1,000 boxes, it might not be as relevant as here with 10. There's many factors to consider with these types of problems. For instance, how large is your sample? What is the value of your data? Another method of displaying data would be an ordered stem and leaf diagram. Let's have a look and see how they're constructed. For this data set, we're given the length measurements in millimetres for 14 worms, and we're asked to draw an ordered stem and leaf diagram for these lengths. When creating an ordered stem and leaf diagram, first locate the smallest and the largest piece of data. Here, the smallest is 36 and the largest is 57. I can use these two pieces of data to lay out the stem and leaf diagram, as I know that the central stem will be made of 3, 4 and 5, as no leaf is smaller than 36 or larger than 57. I can now start to add the rest of my data, beginning with the top, 6, 7 and 9. To represent the 30s, we can then move on to the 40s and the 50s like this. I tend to circle them as I'm completing the diagram so I can see the numbers rather than crossing them out. In order to complete the diagram, I require a key, which I'll place in the top right-hand corner. This is to say that 3 line 6 equals 36, and shows that the number to the left of the central stem and the number to the right will combine to form a 2-digit number. With this stem and leaf diagram, there's three numbers with quantities of 2, 41, 47 and 52. So we can say that this data set is trimodal. If we were asked for the median, again we could tick off the data from either end, now that they're in order, or we can find the place of the median, which will be 14 plus 1 and divided by 2 to get the 7.5th place. So we know it's between the 7th and 8th place, which will be between 43 and 44, so we add them together, divide by 2 to get 43.5. The range would be 57 take away 36 to give us a range of 21, and suggests that we've got quite a wide range of worm lengths, so not a great deal of consistency. Next, we'll look at how they can group large amounts of data together to enable us to use and interpret it. Here, we have a table of data which we are told represents a quality check in a factory that produces packets of mints, and it gives us the following data from 100 samples. We're looking to calculate the averages and the range for this set of data. In the column for the number of mints in each packet, we have 29, 30 or 31. Next, we have the frequency of those quantities. So the number of packets with 29 mints is 23, the number of packets with 30 mints in is 61, and the number of packets with 31 is 16. With this table, calculating the mode is quite simple, because we just read the table and see that there are a far greater number of packets with 30 mints in than either of the other two. So we can state this is the mode, 30 mints per packet. For the median, if we have 100 pieces of data, then 100 plus 1 divided by 2 tells us that we're looking between the 50th and 51st piece of data for the median. As there's only 23 pieces of data in the first category of 29 and 61 in the second, we know that both the 50th and 51st piece of data will be 30, therefore a packet with 30 mints in. We can say that this is therefore our median number in a packet of mints. To calculate the mean average, we firstly need the total number of mints in all of these packets, and then the amounts of packets of mints. We know the second piece of data by adding up the frequency column together to get 100, which is also confirmed in the question itself. In order to find the first piece of information, which is the total mints, we should find the total in each category and then add them together to get an overall total. So we'll do 29 times 23 to give 667, 30 times 61 to give 1830, and 31 times 16 to give 496, which when added together will give us 2993. If we divide this by the frequency of 100, we get 29.93 minutes per box. Let's look at our range to tell how accurate this is. The largest piece of data is 31, and the smallest is 29, which means the range is only 2. In comparison to the total minutes, it's quite small. This, combined with the fact that all of our averages are very similar, leads us to conclude that our averages are quite accurate. Next, we'll look at how they can group data together in a table. Here, we have the data from a survey completed on 80 factory workers, about how many minutes they spent eating their lunch, and it's produced the following data set. We're now asked to calculate an estimate of the mean average time spent eating their lunch. The reason this is an estimate is we don't know where in the range these pieces of data sit. Are they at the top or the bottom of the group boundary? As this is unknown, we need to roughly work it out by taking an estimate of each group interval. This is called the midpoint. For these groups, that would be 5, 15, 25, 35, and 45. We can now estimate the total time taken by each group interval for their lunch by multiplying the frequency by the midpoint of that group. So, 5 times 5 gives us 25, 12 times 15 gives us 180, 32 times 25 gives us 800, and 20 times 35 gives us 700. Lastly, 11 times 45 gives us 495. If we add all these together, we get 2,200. We should remember that the mean is calculated by the total value of the data, 2,200 minutes, divided by the amount of pieces of data. There are 80 workers. 2,200 divided by 80 gives us 27.5 minutes. So we can say the average time they spent eating their lunch was 27.5 minutes. We're also asked to calculate the median class interval, which will be the one with the middle piece of data in it. As there's 80 pieces of data, we can calculate the median by 80 plus 1 divided by 2. This means that we need to be looking for between the 40th and 41st piece of data. As the category which is greater than 20 and up to and including 30 contains from the 18th piece of data to the 59th, we can assume that the median is in it. Therefore, we can state that the median class interval is greater than 20 up to and including 30. To judge the modal class interval, we can quite simply look for the class interval with the most pieces of data in it. And we can see this is also the category greater than 20 up to and including 30. In this video, we looked at how to calculate the mean, median, and mode averages, and the range from a set of data, as well as drawing stem and leaf diagrams, and looking at how to calculate averages from tables and from grouped data charts. In the next video, we'll be looking at sampling and scatter graphs. I'll see you then.